Today we're going to learn about the calculus of hyperbolic functions. Hyperbolic functions might be something you're not familiar with, so I'm going to define what the hyperbolic sine function is and what the hyperbolic cosine function is. So the hyperbolic sine function is defined by e to the x minus e to the negative x divided by 2. And the hyperbolic cosine function is found by finding e to the x plus e to the negative x divided by 2. So basically, if we, roughly speaking, the hyperbolic cosine function is the average of exponential growth and exponential decay, while the hyperbolic sine function represents half the distance between the two phenomenons. So the hyperbolic functions are important in applied problems. You'll use this a lot in physics and engineering. We're just going to basically introduce the topic in this course. So, if I want to find the definition of the hyperbolic functions, I've already given you the hyperbolic sine and the hyperbolic cosine definition, so I'll just rewrite this down here. Now I want to look about what is the tangent, the hyperbolic tangent function. Well, just like in trig, it's the hyperbolic sine function divided by the hyperbolic cosine function. Cosecant is the 1 over the hyperbolic sine function, and secant is 1 over the hyperbolic cosine function. And cotangent is the hyperbolic cosine function over the hyperbolic sine function, which is equal to 1 over the hyperbolic tangent function. Again, of course, that, we can't divide by 0. So let's just look at a few graphs. You do not have to memorize these graphs for this class. I'm just going to basically introduce these so you have an idea what each of these graphs look like. And you can use this space here to sketch each of the graph. You might want to pause a little bit. So this is what a hyperbolic sine function looks like. Notice that our y-axis is our trig values. Here is our hyperbolic cosine function. It looks similar to a parabola shape with a vertex at 0, 1. Then you see our hyperbolic tangent function. Kind of reminds me of a cube root function. Just different axes measurements. Now we have the hyperbolic cosecant function. Some people think of this as kind of looking rational in shape. And our hyperbolic secant function, I love that one, it's just a little hump. And then last but not least, our hyperbolic cotangent function. Now we also need to do some operations with hyperbolic functions, so we need to look at some identities. So if we're thinking about the Pythagorean identities we learned in trig class, we have some that are kind of similar in the hyperbolic realm. So the hyperbolic cosine squared minus hyperbolic sine squared equals 1. The hyperbolic tangent squared plus the hyperbolic secant squared is equal to 1. And then the hyperbolic cotangent squared minus the hyperbolic cosecant squared is equal to 1. Those are kind of like our Pythagorean identities equivalent for the hyperbolic function. Now our power reducing functions is the hyperbolic, if we take the square of the hyperbolic sine function, that is equal to negative 1 plus the hyperbolic cosine function of 2x divided by 2. Our hyperbolic cosine function squared is equal to 1 plus the hyperbolic cosine of the double angle 2x divided by 2. And also sometimes you'll need your double angle formulas. The only ones that we're going to focus on is our double angle formulas for hyperbolic sine and hyperbolic cosine. So the hyperbolic sine of 2x is equal to 2 times the hyperbolic sine function times the hyperbolic cosine function. And the one you need is the hyperbolic cosine of 2x is equal to the hyperbolic cosine squared plus the hyperbolic sine squared. And then another time you might also need to do some operations where you need to add or subtract the hyperbolic sine and hyperbolic cosine. So let's look at the sum and difference formulas for the hyperbolic sine and hyperbolic cosine formulas first. So the hyperbolic sum formula, hyperbolic sine of x plus y is equal to hyperbolic sine of x times the hyperbolic cosine of y plus the hyperbolic cosine of x times the hyperbolic sine of y. And then the difference formula for sine is the hyperbolic sine of x times the hyperbolic sine of y minus the hyperbolic cosine of x times the hyperbolic sine of y. The sum formula for cosine is we're going to have the same trig function and the same sign. So the hyperbolic cosine of x times the hyperbolic cosine of y plus the hyperbolic sine of x times the hyperbolic sine of y. And then our difference formula for a hyperbolic cosine is hyperbolic cosine of x times the hyperbolic cosine of y minus the hyperbolic sine of x times the hyperbolic sine of y. So these are slightly different. The sines, SIGNs, are a little bit different than you learned in the regular trig class. So you need to kind of know the distinctions. All right, what is the derivative? So these are just some derivative formulas to memorize. I'm going to use the chain rule because we use this a lot with a chain rule. So I'm going to, instead of do x, I'm going to use the u. So you always remember, multiply by the derivative of the inside. So the derivative of the hyperbolic sine is a hyperbolic cosine. The derivative of hyperbolic cosine is hyperbolic sine. The derivative of tangent is the hyperbolic secant squared. And the derivative of the hyperbolic cotangent is equal to negative the hyperbolic cosecant squared u, and then of course times du. And then the hyperbolic secant's derivative is negative the hyperbolic secant times the hyperbolic tangent times our derivative of the inside function. The hyperbolic cosecant is also negative. It's negative the hyperbolic cosecant times the hyperbolic cotangent. Okay, let's look at the other direction. Now if I'm going to find the integral of the hyperbolic cosine, that is equal. The integral of the hyperbolic sine is, hyperbolic cosine is the hyperbolic sine. The integral of the hyperbolic sine is the hyperbolic cosine. The integral of the hyperbolic secant squared is hyperbolic tangent. The integral of the hyperbolic cosecant squared is negative the hyperbolic cotangent of u. And the integral of the hyperbolic secant times hyperbolic tangent is negative hyperbolic secant. And the integral of hyperbolic cosecant times hyperbolic cotangent is negative hyperbolic cosecant. Okay, so let's find the derivative and integral of some of these. We're going to find the derivative of the hyperbolic sine of x squared minus 3. So I have a chain rule, so I have an inside function. So I'm going to look at what my du is. So it's the derivative of x squared minus 3 is just simply 2x. So I'm going to start with the outside function. What is the derivative of hyperbolic sine, which is the hyperbolic cosine, and then we times that by the derivative of the outside. So we would write this as 2x, the hyperbolic cosine of x squared minus 3. Okay, let's see how you did on number 2. Did you remember to use the product rule in this first term? So that's first times the derivative of the second, plus our second term times our derivative of the first, and then minus the derivative of the hyperbolic cosine, which is hyperbolic sine. And then combining like terms, this simplifies down to just simply x times the hyperbolic cosine of x. Now let's do some integrals. And so here I'm going to use u substitution. I'm going to u integration. And so I'm going to replace the x squared with u and replace dx with du over 2x. And so my x's simplify out, and I can factor out my 1/2. And then the integral of the hyperbolic cosine is hyperbolic sine. And then the last thing I need to do is remember to replace that u with our original x value. So I get 1/2 the hyperbolic sine of x squared plus c. Okay, so this one I did not give you the integral of the cotangent, the hyperbolic tangent. So what you had to do is you had to rewrite that using the identities. So this is an example of using the identities. So I would start by replacing the hyperbolic tangent of x with the hyperbolic sine of x over the hyperbolic cosine of x. And then I'm going to use u substitution to evaluate this. So the integral of the hyperbolic sine divided by the hyperbolic cosine. I'm going to let u equal my hyperbolic cosine. And so du is going to be equal to hyperbolic sine of dx. And I did that because I knew I'm going to have to divide by the sine, the hyperbolic sine, and so I could cancel out those. And so the hyperbolic sines cancel out. That leaves me with 1 over my u and du. That's it. Everything else cancels out. Well, I know from Cal 1 that the integral of 1 over u is the natural log of the absolute value of u. And I know that u is the equal to the hyperbolic cosine. And so my answer is the natural log of the hyperbolic cosine of x plus c.